Hey guys, we're going to be continuing with what we talked about yesterday, which is the rational or reciprocal function, depending on which way you want to call it, okay? Now, right here we're staring at a rational function. And the instructions I've given us are find the vertical asymptotes and any removable discontinuity. Okay, so first we talked about what a vertical asymptote was yesterday, alright? Let me give you some more information on vertical asymptotes. Vertical asymptotes are found when the denominator equals 0. Okay, that's how you find a vertical asymptote. It is when the denominator equals 0. So like for this problem, I could just say x plus 1 equals 0, and I know that I have a vertical asymptote at x equals negative 1. Excuse me, sorry about that. At x equals negative 1. Now, so that's how you find vertical asymptotes. Let me tell you something. You can have more than one vertical asymptote. Alright, honestly, you can have several, an infinite amount as far as I'm aware, okay? But there is something else called a removable discontinuity, alright? Let's talk about that real fast. A removable discontinuity is just the idea that since this is a fraction, guys, that's what rational means, it means fractional, okay? It means that, hey, if there's something I can cancel out on top and bottom, that means I can remove it because I can cancel it out on top and I can cancel it out on bottom. So when you look at this guy, negative 2 divided by x plus 1. Is there anything I can cancel out there? No. So there is no removable discontinuity. Okay? But if there had been, I would have a removable discontinuity. Let's look at a problem where I might have a removable discontinuity. Okay, so here's a problem that is actually not going to end up with a vertical asymptote, and it is going to end up with a removable discontinuity. Let's talk about it. Okay? So first, when you look at this problem, you might be tempted to say, but Mr. Netherland, you said to find the vertical asymptote, all I have to do is set the denominator equal to 0. Yes, that's true. But what if you can cancel out the denominator? Then that's not a vertical asymptote. That's a removable discontinuity. Here's what I mean by that. Let me erase all this. Let's look at our numerator real fast. X squared plus x minus 6. I can factor this, right? You should think, oh yeah, tic-tac-toe, that's a quadratic trinomial. We've talked about that for 6 months now. So, you just set it up in the tic-tac-toe format. Alright, two numbers that multiply negative 6x squared but add to x. You're like, oh, that's easy. 3x and negative 2x. And then you ask yourself, x squared and 3x, what do they have in common? X. X squared and negative 2x, what do they have in common? X. X times what is 3x? 3. X times what is negative 2x? Negative 2. Then you go across, and you go across. So this top part could be factored to mean x plus 3 times x minus 2. And then all divided by x plus 3. Now, what do you notice you have on top and bottom? You have x plus 3. So you can cancel that out. So then you're left with just x minus 2. That would be your new, this is what we say our new equation would be, okay? So then, do you see I just canceled something out? That is called a removable discontinuity, since I could cancel something out, okay? So the x value, now the removable discontinuity, what does that look like on a graph? A removable discontinuity is just a hole in the graph. So like look at this problem that we just did. After we canceled out the x plus 3's, what were we left with? X minus 2, right? What does the graph x minus 2 look like? Well, that just looks like a line because it's linear. So it looks something like this, right? Except I came from this, and so I canceled out x plus 3. So that means even though I look like a line now, there's a hole in my graph. The question is, where is this hole in my graph? Well, we can find that hole by first taking what we canceled out, which was x plus 3, setting that equal to 0, solve for x, so x equals negative 3. So we know that when x is negative 3, we're going to have a hole in our graph, so it's going to be somewhere down here. But where's my y value going to be? Well, here's how you get your y value. Is you take your x value, and you plug into your new equation. So negative 3 minus 2, which is negative 5. That's minus. Okay? So the removable discontinuity is located at negative 3, negative 5. So that means 3, 4, 5. Right here in this graph, guys, right here, you don't actually touch that part. So what's actually happening is, and I'm going to draw another one just so you guys can see it a little bit better. What's actually happening is that right here at -3, -5, 1, 2, 3, 4, 5, we have a hole in our graph. And so we have this line that looks something, well, it should really be down a little bit further, but that's okay, because I'm trying to just sketch it real fast for you. But so we have this line that skips over this piece right here, okay, because I was able to remove it. Do y'all see how up here, if you go back to your original equation and you plug in a -3, what is -3 plus 3? 0. That's right. So in other words, that would cause a problem because I would be dividing by 0. And I can't divide by 0. Okay? So, even though I canceled it out, I can't just ignore it. So that's why I have created a hole in the graph. It doesn't create a big asymptote because I was able to cancel it out. Okay, yesterday we talked about how it would create a big asymptote. Alright? But it doesn't create a big asymptote because I was able to cancel it out. But that doesn't mean I can just ignore it. So it creates what we call a removable discontinuity, also aka hole. Alright, you will hear it referred to as hole. Alright, let's do another example. So here's my next example. I want you to do the same two things. I want you to find any vertical asymptotes and any removable discontinuities. So this is what you want to do first. You want to factor first. Okay, you can factor x squared minus 1. Alright, so you put your x squared, you put your -1, you get -x squared, and then 0x. What are two numbers that multiply -x squared but add to 0x? X and -x. Very good, very good. I thought that would take some of y'all a little bit. X squared and x, what do they have in common? X. X squared and x, what are -x? What do they have in common? X. X times what is x? 1. X times what is -x? -1. Go across, go across. So this top part can be factored, meaning x plus 1 times x minus 1. Then, next thing you want to do is see if there's anything you can cancel. In this case, there is. I can cancel out this x minus 1 with this x minus 1. So I'm left with just x plus 1. Okay? So this is my new equation. There's no denominator, therefore there is no vertical asymptote. Doesn't exist for this problem. However, since I canceled something out, I have a removable removable discontinuity. I call it RD. Or you can also call it a hole. That's fine too. Okay? So, what I do is I take what I canceled out and I set that equal to 0. I solve. That gives me x equals 1. That's the x value of your hole. How do I get the y value of your hole? You plug the x value of your hole back into your new equation, the equation you got after canceling stuff out. So that's going to be 1 plus 1, which is just 2. So the location of the hole is at the x value 1 and y value 2. And there is no vertical asymptote for this problem, because after we canceled stuff out, no denominator existed. That's a circle with a line through, just really poor. Okay? Let's do one more problem. Okay, here's the last problem I'm going to do with you. Alright, and again, it's the same question. Find any vertical asymptotes and find any removable discontinuities. So step 1, whenever you have that instruction and it looks like there's something you can factor, that is step 1. You don't always have to factor. There's not always something to factor. Okay? But if you can factor it, you factor it. So let's look at our numerator. 2x squared plus 3x minus 2. That is a perfect factoring situation. It is 3 terms. It is quadratic. So we put the quadratic term first. We put the constant term next. We multiply. That gives us negative 4x squared. We need to add to the linear term, which is 3x. And you're like, two numbers that multiply negative 4x squared, but add to 1x. 4x and... Nope, not 1x. I don't know why I said 1x. Sorry. That's not my linear term. What's my linear term? 3x. So I need two numbers that multiply negative 4x squared, but add to 3x. 4x and negative x. Very good. Now, 2x squared and 4x, what do they have in common? A 2x. Very good. 2x squared and negative x, what do they have in common? X. 2x times what is 4x? 2. X times what is negative x? Negative 1. Go across, go across. So my numerator can now be rewritten as 2x minus 1 times x plus 2. Okay? Divided by, so now we're going to factor our denominator as well. Okay, so we have 2x squared, 1, 2x squared, we're multiplied. We need to add to the linear term, which is negative 3x. What are two numbers that multiply 2x squared but add to negative 3x? That's right, negative 2x and negative 1x. Okay, 2x squared and negative 2x, what do they have in common? 2x. 2x squared and negative x, what do they have in common? X. 2x times what is negative 2x? Negative 1. X times what is negative x? Negative 1. We go across, we go across. So this guy can be factored down to being 2x minus 1 times x minus 1. Awesome. Okay. So now, is there anything I can cancel out? Yes, the 2x minus 1s. So it's gone. I crossed them out. I canceled out. So I'm left with x plus 2 divided by x minus 1. This should be sending off alarm bells. I just canceled something out. That means I have a removable discontinuity. What did I just cancel out? The 2x minus 1s. So I set 2x minus 1 equal to 0, and I solve for x. Add 1, divide by 2, so you get x equals 1/2. That is the x value of your hole, the location of your hole. You now need the y value, because remember, the hole is just a point. It's a point I don't get to include. Okay, that's all a removable discontinuity is. It's just a point I do not get to include. So that means it has an x value and a y value. So this is my x value, 1/2. Okay, I plug into my new equation. So that's going to be 1/2 plus 2 divided by 1/2 minus 1. If you're not a big, fraction person, that's fine. Cheat and use a calculator. There's absolutely nothing wrong with that. I use the word cheat, but, it's not actually cheating. All right. So 0.5 plus 2 divided by 0.5 minus 1. Press enter, and we get negative 5. So that means the x and y value, the x value was 1/2. The y value is negative 5. Bam, that's your hole. But wait, do you still have a denominator? Yes, that means you also get to have a vertical asymptote. How do I find my vertical asymptote? Set your denominator equal to 0. So x minus 1 equals 0. Add 1, x equals 1. Bam, that is your vertical asymptote. X equals 1. This is your hole, 1/2 negative 5. Okay? Guys, I know this video turned out to be a little bit longer than I planned. I really hope I explained everything well. I tried to go slow. Please send me a reminder with any questions. Please just, if you need to come by after school today, I will be there. Have a great day.